Beneath the cracked frozen surface of Europa lies an ocean containing more water than every sea on Earth combined. That single fact has made this moon the most tantalizing destination in the search for life beyond our planet. But here is what nobody tells you. That ocean is buried under an ice shell recently measured at approximately 18 miles thick. The surface above it is blasted by radiation from Jupiter's magnetosphere so intense that an unshielded human would absorb a lethal dose within a single day. The temperature never climbs above minus 160 degrees Celsius. The atmosphere is a vacuum, and the gravity would slowly dissolve your bones. Europa is not a paradise hiding beneath ice. It is a frozen radiation trap surrounding an ocean you cannot reach. If you enjoy journeys that completely reshape how you think about the universe, do me a favor and hit that like button or subscribe. It genuinely helps this channel bring you more deep dives like this one, and I appreciate every single one of you who sticks around. Now, settle in, get yourself comfortable, let's begin. Start with a photograph of Europa taken by the Galileo spacecraft in the late 1990s. Not a painting, not an artist's impression. An actual image captured from orbit around Jupiter. What you see is a world that looks like nothing else in the solar system. The surface is almost perfectly smooth. No towering mountains, no deep craters. Instead, the entire moon is wrapped in a shell of water ice so bright that it reflects nearly 70% of the sunlight that touches it. Cutting across that brilliant white surface is an intricate web of reddish-brown lines, fractures that crisscross the globe like veins on a marble. Some of these cracks stretch for hundreds of kilometers, others branch and intersect in patterns so complex that geologists spent years trying to classify them. And scattered between the ridges are regions of shattered, jumbled terrain, where the surface appears to have collapsed and refrozen into chaotic blocks of ice, tilted at strange angles like broken sheets of glass reassembled by a careless hand. This is Europa, the smallest of Jupiter's 4 large moons, a body slightly smaller than Earth's own moon, roughly 3,100 kilometers across. And for the past several decades, this frozen world has quietly become the single most compelling destination in humanity's search for life beyond Earth. The reason is water, not the frozen kind visible on the surface. That ice shell is interesting, but ice alone does not make a world special. What makes Europa extraordinary is what the ice is hiding. Every major line of evidence, gathered across multiple missions and decades of observation, points to the same conclusion. Beneath that cracked, frozen exterior lies a global ocean of liquid salt water that may contain more than twice the volume of all the oceans on Earth combined. The first serious hints came from the Voyager flybys in 1979. Voyager 1 and Voyager 2 passed through the Jupiter system and returned images of Europa that puzzled scientists immediately. The surface was suspiciously young. On most solid bodies in the solar system, craters accumulate over billions of years. The older the surface, the more impacts it shows. Europa had almost none. The visible surface appeared to be no more than 40 to 90 million years old. A geological blink. Something was erasing the craters. Something was resurfacing the moon. The real breakthrough arrived with the Galileo spacecraft, which orbited Jupiter from 1995 to 2003. Galileo carried a magnetometer that detected something remarkable. As Europa moved through Jupiter's powerful magnetic field, it generated a secondary magnetic signal, an induced field that varied in a pattern perfectly consistent with a layer of electrically conductive fluid beneath the surface. Ordinary ice does not conduct electricity well enough to produce that signal. Salt water does. The magnetometer data became the strongest single piece of evidence for a subsurface ocean, and it has never been seriously challenged. Subsequent analysis of Europa's gravity field and tidal flexing supported the same conclusion. Europa is not a solid ball of rock and ice. It is a layered world with a metallic core, a rocky mantle, and a thick outer shell composed of ice above and liquid water below. The ocean exists because of heat, and that heat comes from an unlikely source. Europa orbits Jupiter at a distance of roughly 671,000 kilometers, locked in a gravitational relationship with 2 neighboring moons, Io and Ganymede, called the Laplace resonance. Their orbital periods are locked in a ratio of 1 to 2 to 4. Every time Io completes 4 orbits, Europa completes 2, and Ganymede completes 1. This precise synchronization prevents Europa's orbit from becoming perfectly circular. The slight eccentricity that remains means Jupiter's gravitational pull varies as Europa moves closer and farther from the planet during each orbit. That variation flexes the entire Moon, squeezing and stretching its interior like a stress ball in a giant hand. The flexing generates friction, the friction generates heat, and that heat, called tidal heating, is enough to keep a vast volume of water in a liquid state, despite surface temperatures that would freeze carbon dioxide solid. Tidal heating does more than simply maintain the ocean. It likely drives geological activity at the boundary between the rocky interior and the liquid water above. On Earth, wherever hot rock meets ocean water, hydrothermal vents form. These vents release chemical energy and mineral-rich fluids into the surrounding water, creating ecosystems that thrive in complete darkness, independent of sunlight. If similar processes occur on Europa's seafloor, and the physics suggests they could, then the ocean may possess not just water, but a continuous source of chemical energy. That combination, liquid water plus chemical energy plus a rocky interface where reactions can occur, represents the fundamental recipe for habitability as scientists currently understand it. Recent observations have strengthened this picture. In 2023, the James Webb Space Telescope detected carbon dioxide ice on Europa's surface, concentrated in a region of chaos terrain called Terra Regio. 2 independent research teams analyzed the data and reached the same conclusion. The carbon dioxide appeared to originate from within Europa, most likely from the subsurface ocean itself. Carbon is one of the essential building blocks of life as we know it. Finding evidence that it exists inside the ocean was a significant step. It meant the ocean was not just water. It contained at least some of the chemistry that biology requires. Meanwhile, Jupiter's radiation belts were doing something unexpectedly useful on the surface. Charged particles trapped in Jupiter's magnetosphere, mainly high-energy electrons and protons, constantly bombard Europa's ice. This bombardment splits water molecules apart through a process called radiolysis, producing molecular oxygen and hydrogen. The hydrogen escapes into space because Europa's gravity is too weak to retain it. Some of the oxygen lingers in a tenuous atmosphere, while the rest becomes trapped in the surface ice. Scientists hypothesized that if this radiation-processed surface material could somehow reach the ocean, it might provide oxidants, chemical fuel that organisms could potentially use for energy. In 2024, NASA's Juno spacecraft delivered the first direct measurement of how much oxygen Europa's surface actually produces. The result was surprising. The JADE instrument aboard Juno detected charged oxygen and hydrogen ions during a close flyby in 2022, and the team calculated an oxygen production rate of approximately 12 kilograms per second. That is roughly 1,000 metric tons per day. It sounds like a lot until you compare it to earlier estimates, which ranged from a few kilograms per second to over 1,100 kilograms per second. The actual measurement fell at the low end. Europa was producing far less oxygen than many models had predicted, which narrowed the range of oxygen potentially available to feed any biology in the ocean below. Then came another complication. For over a decade, one of the most exciting possibilities about Europa was that it might be venting material directly from the ocean into space, through water vapor plumes, similar to the dramatic geysers observed on Saturn's moon Enceladus. In 2012 and 2013, observations from the Hubble Space Telescope appeared to detect faint ultraviolet emissions near Europa's south pole, consistent with plumes of water vapor rising to altitudes of roughly 200 kilometers. If confirmed, such plumes would offer a way to sample ocean material without ever drilling through the ice. A spacecraft could simply fly through the spray and analyze what it collected, but the evidence proved frustratingly elusive. Subsequent Hubble observations through 2020 failed to detect the emissions again. The James Webb Space Telescope searched for plume signatures and found nothing. And in 2026, the original research team conducted a comprehensive reanalysis of 14 years of Hubble data. Their conclusion, published in Astronomy and Astrophysics, was sobering. The statistical confidence in the original detection dropped from 99.9% to less than 90%. The lead author acknowledged that the original signal may have been a statistical artifact. The plume hypothesis is not dead, but it is no longer the near certainty it once appeared to be. Europa may not be offering easy access to its ocean after all. While the plume debate continued, other observations were quietly revealing what Europa's surface is actually made of. The reddish-brown material filling the moon's fractures and chaos regions is not just dirty ice. Spectroscopic analysis from the Galileo spacecraft and later Hubble Space Telescope observations identified irradiated salts, including sodium chloride, the same compound found in Earth's table salt, and magnesium sulfate. Jupiter's radiation processes these salts continuously, breaking them apart and recombining them with the surrounding ice to produce sulfuric acid hydrate and other compounds that stain the surface in distinctive reddish and yellowish-brown hues. The distribution of these materials is not random. Sodium chloride concentrations appear highest in the youngest, most geologically disrupted terrain, the same chaos regions where the James Webb Space Telescope later found carbon dioxide. This pattern suggests that the salts were emplaced from below, brought to the surface through geological activity that exposed material originating from the ocean. If that interpretation is correct, the chemistry visible on Europa's surface is a degraded, radiation-processed echo of the ocean's own composition. Every fracture stained with salt is a potential fingerprint of the water hidden beneath, altered beyond easy reading by billions of years of bombardment, but still carrying information about what lies below. And then came the measurement that changed the entire conversation about what reaching that ocean would actually require. In late 2025, results from Juno's microwave radiometer were published in the journal Nature Astronomy. During the 2022 flyby, the instrument had peered beneath Europa's surface using microwave frequencies that penetrate ice far deeper than visible light. The data revealed the thermal structure of the upper ice shell and allowed the team to calculate its thickness. For the idealized case of pure water ice, the shell averages approximately 29 kilometers thick, plus or minus 10 kilometers. That is roughly 18 miles of solid frozen barrier between the surface and the ocean. To understand what that number means, consider the context. For years, scientists debated whether Europa's ice shell was thin, perhaps only a few kilometers, or thick, potentially tens of kilometers. A thin shell would mean the ocean was relatively accessible. Cracks might penetrate all the way through, plumes might erupt easily. Future missions might be able to melt their way down in a matter of months. A thick shell would mean the opposite. The ocean would be sealed away beneath a frozen fortress that no existing technology could breach on any reasonable timeline. The Juno measurement decisively favors the thick shell model. 29 kilometers of ice is not a minor obstacle. It is a barrier on a scale that dwarfs any drilling project ever attempted on Earth. The deepest borehole humans have ever created, the Kola superdeep borehole in Russia, reached just over 12 kilometers into rock after nearly 20 years of continuous effort. And that was on Earth, with unlimited power, full atmospheric pressure, stable temperatures, road access for heavy equipment, and a team of engineers who could go home at night. On Europa, a drill or thermal probe would need to descend more than twice that distance through ice, operating on battery or reactor power, in a vacuum, at temperatures that would freeze most lubricants solid, with no possibility of resupply, repair, or rescue. A separate 2026 study, published in the Journal of Geophysical Research, modeled the ice shell's evolution over time and found a thickness range of 20 to 45 kilometers, depending on tidal heating rates and ice viscosity. If a warmer, convective layer exists beneath the rigid conductive lid, as many scientists suspect, the total shell could be even thicker than what the microwave radiometer measured. The most optimistic reading of the data still places the ocean beneath at least 15 to 20 kilometers of ice. The pessimistic reading pushes it past 40. This is the first fracture in the dream of Europa. The ocean is real. The evidence for that is overwhelming and comes from multiple independent sources. But the ocean is not lying just beneath the surface waiting to be tapped. It is buried under a frozen shield so thick that accessing it represents one of the most formidable engineering challenges imaginable. The ice does not cooperate. It is not uniform. It contains fractures, pores, and possibly pockets of briny slush. But these features exist within a matrix of frozen material that extends downward for distances measured in tens of kilometers. The cracks visible on the surface, those dramatic reddish-brown lines that make Europa look so geologically active, do not appear to penetrate anywhere close to the ocean. They are surface and near-surface features, not highways to the deep. Now, layer on the surface conditions. Europa has an atmosphere, technically. Its surface pressure is approximately 1/10 of a micropascal, roughly 1/trillionth of Earth's atmospheric pressure at sea level. For all practical purposes, it is a vacuum. There is no air to breathe, no pressure to keep your blood from boiling, no medium to carry sound. Standing on Europa's surface would be functionally identical to standing in open space, except the ground beneath your feet would be ice, and the radiation would be worse. The temperature is savage. At the equator, the warmest point on the moon, surface temperatures never rise above approximately -160 degrees Celsius. At the poles, they drop to -220 degrees Celsius. These are not conditions that simply require warm clothing. At -160 degrees Celsius, most metals become brittle. Rubber shatters like glass. Standard lubricants freeze solid. Electronics designed for room temperature fail catastrophically. Every piece of equipment, every tool, every structural component brought to Europa would need to be engineered from scratch to survive temperatures that most materials were never designed to endure. And then there is the radiation. Jupiter possesses the most powerful magnetosphere of any planet in the solar system, a vast magnetic field generated by the planet's rapidly spinning metallic hydrogen interior. This magnetosphere traps enormous quantities of charged particles, primarily high-energy electrons and ions, in radiation belts that extend millions of kilometers from Jupiter. Europa orbits deep inside these belts. The moon's surface is continuously bombarded by a torrent of energetic particles that interact with the ice, producing the radiolysis effects described earlier. But what creates interesting chemistry for potential ocean microbes creates lethal exposure for human beings. Radiation dose rates on Europa's surface vary significantly by location. The harshest zones are concentrated in broad oval-shaped regions around the equator, where the geometry of Jupiter's magnetic field channels the most intense particle flux. The dose decreases toward the poles, but even the mildest regions receive radiation levels that would be dangerous to human tissue over short exposures. To put this in human terms, NASA's current career radiation exposure limit for astronauts is 600 millisieverts accumulated over an entire career in space. On Europa's surface, in the most irradiated equatorial zones, an unshielded human could accumulate a dose exceeding that full career limit within a matter of hours. Sustained exposure over a single day could approach or exceed the 4 to 5 sievert threshold that is lethal to roughly half of all exposed individuals within 30 days without medical treatment. This is not a problem you solve with a thicker spacesuit. High-energy electrons and protons at the energies present in Jupiter's radiation belts penetrate most conventional shielding materials. Even the Europa Clipper spacecraft, currently en route to Jupiter after launching in October 2024, was designed to avoid prolonged exposure. The mission plan calls for 49 close flybys of Europa, rather than direct orbit, precisely because orbiting the Moon would expose the spacecraft to cumulative radiation doses that would rapidly degrade and eventually destroy its electronics. The spacecraft carries a shielded vault of aluminum and titanium to protect its most sensitive instruments, and even with that protection, radiation management is one of the mission's defining engineering constraints. Europa Clipper is expected to arrive at Jupiter in April 2030. The European Space Agency's JWST mission, which launched in April 2023, will arrive the following year. Together, these missions will study Europa's ice shell, surface composition, and geology in unprecedented detail. But neither mission will land, neither will attempt to drill, neither will enter the ocean. They will observe from a distance, gathering data that will refine our understanding of what lies below. The actual exploration of Europa's ocean remains a challenge for a future generation of technology that does not yet exist. Europa's gravity adds a final layer of difficulty. The Moon's surface gravity is approximately 1.3 meters per second squared, roughly 13% of Earth's. You would weigh about 1/7 of what you weigh at home. This sounds liberating until you consider the long-term consequences. Every study of reduced gravity environments, from International Space Station missions lasting 12 months or more, shows significant bone density loss, muscle atrophy, and cardiovascular deconditioning. Those studies were conducted in microgravity, not partial gravity, and scientists still do not fully understand how partial gravity environments between 0 and 1G affect human health over periods of years. There is no data. No human has ever lived in 13% gravity for any length of time. The effects on pregnancy, childhood development, and long-term organ function are entirely unknown. What is known is that human physiology evolved under 1G and deteriorates measurably when that force is removed. So here is what Europa actually offers a human settler, an ocean that probably exists, containing more water than Earth, potentially harboring the chemical conditions relevant to life, sealed beneath somewhere between 15 and 45 kilometers of ice that no human technology can currently penetrate. A surface exposed to radiation intense enough to deliver a lethal dose within a day of unshielded exposure, temperatures that would destroy most human-rated equipment, atmospheric pressure indistinguishable from the vacuum of space, gravity so weak it would steadily degrade the human body, and a distance from Earth so vast that even light takes between 33 and 53 minutes to make the one-way trip, meaning that by the time you call for help and receive an answer, nearly 2 hours have passed. Europa is not a habitable world with a frozen lid. It is a scientific treasure buried inside one of the most hostile environments humans have ever contemplated entering. And the next question is the one that matters most. If anyone ever attempted to live there anyway, what would that life actually look like? What would it take to build a habitat that could survive the radiation, the cold, the vacuum, the isolation, and the punishing distance from everything humans have ever known? The answer is worse than you think. Forget everything you have seen in science fiction about living on other worlds. The domed cities, the glass-walled observation decks, the elegant habitats perched on alien ridgelines with panoramic views of a foreign sky. None of that applies to Europa. Not a single architectural feature designed around the human desire to see, to stand in open space, to feel connected to the landscape outside, would survive the first hour on this moon. A habitat on Europa would not be a place to admire the view. It would be a bunker designed around a single overwhelming requirement, keeping its inhabitants alive long enough to justify the cost of sending them there. But before anyone builds anything on Europa, they have to get there, and getting there is its own ordeal. Europa orbits Jupiter at roughly 5.2 astronomical units from the Sun. From Earth, the distance to Jupiter ranges from approximately 600 million kilometers at closest approach to nearly 1 billion kilometers at its farthest. No direct trajectory from Earth reaches Jupiter quickly. The Europa Clipper spacecraft, which launched in October 2024, will not arrive until April 2030, a cruise phase of approximately 5.5 years. That mission uses gravity assists from Mars and Earth to gain sufficient velocity. A crewed mission would follow a similar timeline. Depending on trajectory design, propulsion technology, and the alignment of planetary orbits at launch, the transit to Jupiter could take anywhere from roughly 3 years using advanced propulsion concepts to over 6 years using conventional chemical rockets with gravity assists. 6 years in transit. Think about what that means for a human crew before a single boot touches Europa's ice. The people attempting to settle there would have already spent years confined in a spacecraft. They would have endured the physiological degradation of prolonged weightlessness or partial artificial gravity during cruise. They would have consumed years of their consumable supplies. They would have already experienced the psychological strain of isolation, the signal delay growing longer every day as Earth recedes. By the time they arrive in Jupiter orbit, they are not fresh explorers stepping off a shuttle. They are depleted human beings at the end of a multi-year voyage, about to begin the hardest part. Arrival at Jupiter introduces a new set of hazards. The spacecraft must decelerate from its interplanetary trajectory and enter orbit around Jupiter, a maneuver requiring substantial fuel and precision. Jupiter's gravity well is enormous, the deepest of any planet in the solar system. The insertion burn must be timed exactly to achieve the correct orbital parameters. A failure during this phase could send the spacecraft on a trajectory that misses Jupiter entirely, overshoots into a collision course, or enters an orbit from which there is no recovery. The crew has one attempt. There is no abort to Earth option at Jupiter distance. Once in Jupiter orbit, the spacecraft must navigate to Europa, which introduces the radiation problem immediately. Jupiter's magnetosphere extends millions of kilometers from the planet. Any orbit that brings the crew close to Europa passes through the most intense radiation belts. Transit time within those belts must be minimized, which constrains the available approach trajectories and landing windows. Landing on Europa itself presents challenges with no direct precedent. Mars landings benefit from an atmosphere that allows parachutes and aerodynamic deceleration. Lunar landings benefit from decades of experience and proximity to Earth for real-time support. Europa has neither. The atmosphere is a vacuum. There is no aerodynamic braking. The entire descent must be performed using retro-propulsion, firing rocket engines downward to slow the spacecraft against Europa's gravity. The gravity is low, only 13% of Earth's, which helps reduce the fuel required but also makes the landing dynamics unfamiliar. Every Mars lander ever built was designed for 38% gravity. Every lunar lander was designed for 16%. 13% is lower than either, meaning the spacecraft descends slowly but corrections must be precise. The surface itself is ice, not rock. Landing pads designed for rocky terrain might behave differently on a frozen surface that could be uneven, cracked, or concealing subsurface voids. A lander leg punching through a thin ice crust into a buried gap would be catastrophic. And through all of this, the radiation clock is running. Every minute the crew spends on or near the surface before shielding is in place adds to their cumulative dose. The landing must be fast. The transition to shelter must be faster. This brings us to the constraint that dominates everything once the crew is on the ground: radiation. Jupiter's magnetosphere is the largest coherent structure in the entire solar system. If you could see it, it would stretch across the sky wider than the full moon as viewed from Earth. The magnetic field originates deep inside Jupiter, generated by currents flowing through a layer of metallic hydrogen compressed under pressures so extreme that the element behaves like a liquid metal. This field rotates with the planet, completing one full turn every 10 hours, and it sweeps through a vast volume of space extending millions of kilometers in every direction. Trapped within this field are enormous populations of charged particles, mainly electrons, protons, and heavier ions stripped from Io's volcanic atmosphere and accelerated to tremendous energies by the rotating magnetic field. Europa orbits inside this radiation environment at a distance of roughly 671,000 kilometers from Jupiter. The Moon sits deep within the most intense radiation belts, bathed in a constant flux of particles that have been accelerated to energies measured in millions of electron volts. These particles slam into Europa's surface ice at speeds approaching the speed of light. When they hit, they penetrate the top few centimeters to roughly a meter of ice, depositing their energy as they slow down. This process produces the radiolysis chemistry discussed earlier, but from a human perspective, the same particles that create interesting chemistry in ice create catastrophic damage in living tissue. Radiation harms biological systems by breaking chemical bonds, particularly in DNA molecules. High-energy electrons and protons rip through cell structures, severing the molecular strands that carry genetic information. At low doses, the body can repair this damage. At higher doses, the repair mechanisms are overwhelmed. At the dose rates present on Europa's surface, an unshielded human body would accumulate damage faster than any biological repair process could compensate. The equatorial zones receive the worst exposure, but even the comparatively milder polar regions would be dangerous over anything more than a brief visit. This means a Europa habitat cannot sit on the surface exposed to the sky. It cannot have windows. It cannot feature outdoor walkways or observation platforms, or any structure that places a thin barrier between the interior and Jupiter's particle bombardment. The habitat must be buried. The most practical shielding strategy involves placing the entire habitable structure beneath several meters of ice or regolith. Water ice is a reasonably effective radiation shield because hydrogen atoms are efficient at slowing and absorbing high-energy particles. The ice on Europa's surface is abundant, essentially unlimited, and already in place. Burying a habitat beneath approximately 3 to 5 meters of compacted ice would reduce the radiation dose inside to levels comparable to what astronauts experience aboard the International Space Station, roughly a few hundred millisieverts per year, rather than multiple sieverts per day. Deeper burial would provide even greater protection. But burial creates its own problems. Construction becomes vastly more complex when every module must be positioned underground. On the Moon or Mars, you can at least assemble structures on the surface and then pile regolith over them. On Europa, the extreme cold makes ice behave more like rock. At -160 degrees Celsius, water ice has a compressive strength comparable to granite. You cannot shovel it, you cannot scoop it, you must cut it, melt it, or blast it, all of which require energy that must come from a power source you have not yet installed. The construction sequence becomes a circular dependency. You need shielding to work safely on the surface. You need to work on the surface to build the shielding. Every early construction crew member would be accumulating radiation exposure during the setup phase, racing against their own biology to get the habitat buried before cumulative dose becomes dangerous. One approach would be to use robotic systems for the initial construction, remotely operated machines that excavate trenches or tunnels in the ice, place prefabricated habitat modules, and then fill in the shielding material above and around them. But remote operation from Earth is impractical. The one-way communication delay between Earth and Jupiter ranges from roughly 33 minutes when the planets are closest to approximately 53 minutes when they are farthest apart. A round-trip signal takes over an hour at minimum and nearly 2 hours at maximum. You cannot teleoperate a robot with that kind of lag. Every command you send describes a situation that ceased to exist an hour ago. The robot must either operate autonomously or be controlled by crew members already on site, which returns you to the radiation exposure problem. Even after the habitat is buried and shielded, the radiation does not simply vanish. Secondary radiation is generated when high-energy particles interact with shielding material. Primary cosmic rays and magnetospheric particles striking the ice above the habitat produce showers of secondary particles, including neutrons, which penetrate deeper than the original radiation. Effective shielding design must account for these secondary effects, incorporating layers of different materials to absorb both primary and secondary radiation. The habitat walls would likely need composite construction, combining ice shielding on the exterior with denser materials like polyethylene or metal alloys closer to the living space to catch stray neutrons and gamma rays. Every kilogram of dense shielding material must be transported from Earth at enormous cost or manufactured on site from local resources, which adds another layer of industrial infrastructure that must somehow be established in a lethal environment. Now consider power. Every function of the habitat depends on electricity. Heating, lighting, air recycling, water purification, food production, communications, radiation monitoring, medical equipment, computing, robotic maintenance, and the operation of whatever drilling or scientific equipment the settlement uses. Without continuous, reliable electrical power, every person inside the habitat dies. There is no margin. There is no backup plan that does not involve electricity. Power failure on Europa is not an inconvenience. It is an extinction event. Solar energy is functionally useless at Jupiter's distance from the Sun. Europa receives approximately 50 watts of solar energy per square meter, compared to roughly 1,360 watts per square meter at Earth's distance. That is less than 4% of what solar panels receive on Earth. Even the most efficient panels ever manufactured would generate a trickle of power under these conditions. And that trickle assumes clear line of sight to the Sun, which a buried habitat does not have. Solar panels would need to be placed on the surface, exposed to the very radiation the habitat is designed to avoid. Jupiter's charged particles degrade solar cell performance over time, reducing output and eventually destroying the panels entirely. The Europa Clipper spacecraft uses the largest solar arrays ever built for a planetary mission, spanning roughly 25 meters tip to tip, and those are rated for a limited operational lifetime precisely because of radiation degradation. A permanent settlement cannot rely on technology that self-destructs. The only viable power source is nuclear fission. A compact reactor fueled by enriched uranium could provide continuous electrical and thermal energy for years without refueling. NASA has been developing small fission reactor designs for deep space applications, including the KiloPower project, which demonstrated a 1 kilowatt prototype and is being developed toward full-scale designs capable of producing up to 10 kilowatts of electrical power. A Europa settlement would likely require multiple such reactors providing hundreds of kilowatts or more, with redundant backup systems to ensure that no single point of failure could shut down the entire habitat. But reactors are heavy. They require radiation shielding of their own, separate from the habitat shielding, to protect the crew from the reactor's neutron and gamma emissions. They produce waste heat that must be managed carefully in an environment where radiating heat into space is efficient, but losing heat to the ice beneath you could cause the habitat to slowly melt its own foundation. They require cooling systems that must function flawlessly at temperatures where most coolant fluids would freeze, and they must be maintained. Moving parts wear, control systems age, fuel elements degrade. On Earth, nuclear reactors are maintained by teams of hundreds of specialized engineers with access to global supply chains. On Europa, a handful of crew members would be responsible for every aspect of reactor operation, maintenance, and emergency response, with no spare parts available closer than 600 million kilometers away. Heating is the quiet killer. Even with a functioning reactor providing electricity, keeping the habitat warm enough for human survival requires continuous energy input. At minus 160 degrees Celsius, the temperature gradient between the interior of the habitat and the surrounding ice is over 180 degrees Celsius. Heat flows relentlessly from warm to cold. The habitat bleeds thermal energy into the ice through every surface of contact. Insulation helps, but cannot eliminate the loss. The habitat must continuously pump heat into the living space to maintain survivable temperatures, and any interruption in that heating, whether from power failure, pump malfunction, or insulation breach, would cause interior temperatures to begin dropping within minutes. In an environment this cold, the thermal mass of the habitat structure would absorb heat from the air almost immediately. Within hours, temperatures inside could fall below the point where water pipes freeze, equipment fails, and exposed skin suffers frostbite. Within a day, the habitat becomes uninhabitable. This is not speculation. This is thermodynamics applied to the known surface conditions. A Europa habitat would operate at the edge of thermal collapse at all times, held in place only by continuous mechanical effort. There is no passive survival state. If the machines stop, the humans die. Communications present their own particular cruelty. The signal delay alone transforms every interaction with Earth into something closer to correspondence than conversation. Ask a question, wait over an hour for a reply, receive an answer to a question you asked about a situation that may have already changed. Real-time consultation with specialists on Earth is impossible. Medical emergencies must be handled entirely by the crew. Engineering crises must be diagnosed and repaired with whatever knowledge and tools are on hand. Psychological support from friends and family takes the form of recorded messages played hours after they were sent, a process that studies of long-duration spaceflight have shown degrades emotional connection over time. But the delay is only part of the problem. Jupiter itself is one of the most powerful radio sources in the solar system. The planet's magnetosphere generates intense radio emissions, bursts of electromagnetic noise created by the same charged particles that irradiate Europa's surface. These emissions can interfere with communications signals, adding static and disruption to already tenuous connections with Earth. Antenna systems would need to be placed on the surface, exposed to both radiation damage and the extreme thermal environment, and oriented to maintain a clear signal path past Jupiter's radio interference. Maintaining those antennas would require surface excursions, which means radiation exposure, which means time limits, which means the communication system that connects the settlement to the rest of human civilization is itself a hazard to the people who depend on it. Food production inside a sealed, buried habitat would depend entirely on artificial agriculture. There is no arable soil on Europa. There is no sunlight reaching the interior. There are no pollinators, no earthworms, no microbial communities that normally sustain plant growth. Every calorie consumed by the crew must be produced inside sealed hydroponic or aeroponic growing chambers, illuminated by artificial light, powered by the nuclear reactor. These systems work. Versions of them have been tested on the International Space Station and in terrestrial analogues, but they are fragile. They depend on precise control of nutrient solutions, lighting cycles, temperature, humidity, carbon dioxide levels, and water purity. A single contamination event, a fungal bloom, a bacterial infection in the nutrient supply, a failure in the lighting system, could destroy an entire crop cycle and leave the crew dependent on stored rations with no way to resupply from Earth for months or years. Assuming a resupply mission is even possible, the variety of food would be severely limited. Leafy greens, some root vegetables, possibly soybeans and wheat in more advanced systems. Meat production is essentially impossible in a small sealed habitat. The crew would eat the same restricted diet for the duration of their stay, which could be measured in years. Nutritional deficiencies, even subtle ones, compound over long periods and contribute to immune suppression, bone loss, and psychological deterioration. The monotony of food is a known stressor in isolated environments. Antarctic research stations, submarine crews, and long-duration spaceflight all report that food variety, or the lack of it, has measurable effects on morale. Water is the supreme irony of Europa. The moon is covered in it. The ice shell contains more frozen water than any human settlement could ever use. Beneath it lies an ocean of liquid water so vast it dwarfs Earth's hydrosphere. And yet, providing clean, usable water to a habitat on Europa would be an engineering project of serious complexity. The surface ice is not pure. Jupiter's radiation has processed it chemically, producing peroxides, sulfuric acid compounds, and various radiolytic products embedded in the frozen matrix. Simply melting surface ice and drinking it would be dangerous. The water must be mined, transported to the habitat, melted using energy from the reactor, purified to remove radiation-produced contaminants, stored under pressure to prevent it from boiling in the near vacuum, and then continuously recycled through the habitat's life support system. Every step in that chain requires functioning equipment, electrical power, and human oversight. Water recycling technology exists and is used on the International Space Station, where approximately 90% of water, including humidity from the air and processed urine, is recovered and purified. But that system operates in a controlled, microgravity environment with regular resupply from Earth. On Europa, the recycling system must operate at near perfection indefinitely, with no resupply, in a radiation-degraded environment where replacement parts are fabricated on site or not at all. Now consider the medical reality, because this is where the isolation becomes most visceral. A Europa settlement's medical module would bear no resemblance to a hospital. It would be a compact compartment containing what amounts to a field surgery kit, a portable ultrasound unit, a limited pharmacy of pre-packed medications, basic laboratory equipment for blood and urine analysis, a small ventilator, a defibrillator, and whatever supplies can be justified within the mission's mass budget. There would be no full-body imaging, no magnetic resonance capability, no computed tomography scanner. These devices weigh hundreds of kilograms each, consume enormous power, and require specialized maintenance that a small crew cannot provide. Diagnosis of internal injuries, tumors, or complex conditions that on Earth would be trivially identified through imaging would have to rely on physical examination, portable ultrasound, and clinical judgment. The pharmacy would be finite and pre-selected years before launch, based on statistical projections of what conditions the crew is most likely to develop. If someone develops a condition that was not anticipated, or if the supply of a critical medication runs out, there is no pharmacy to call, no emergency shipment, no substitute available. The crew's medical officer, who is likely also an engineer, a scientist, and a construction worker, must improvise with what is on hand. Surgical procedures beyond the most basic wound closure and fracture stabilization would carry extreme risk. There is no blood bank. Transfusions would require a compatible donor from within the crew, assuming one exists. Anesthesia in a low-gravity, closed-atmosphere environment introduces complications that have never been tested outside of theoretical models. Post-operative recovery in 13% gravity is an unknown. Consider a scenario as simple as appendicitis. On Earth, this is routine surgery. On Europa, it is a life-threatening emergency managed by a crew member with field surgical training, using limited anesthetic supplies, in a compartment not designed as an operating theatre, with no way to call for expert guidance that arrives in less than an hour. If complications develop during the procedure, the medical officer makes every decision alone. If the patient deteriorates in the hours after surgery, there is no intensive care unit. There is a bunk, a monitoring device, and whatever attention the rest of the crew can spare from the systems that keep everyone else alive. Dental emergencies, which occur routinely in isolated environments, would be managed with portable extraction tools and temporary repair kits. Psychiatric crises, which long-duration isolation research identifies as a significant risk, would be managed by crew members with psychological first aid training but no psychiatric specialization. A crew member experiencing a psychotic episode, a severe depressive crisis, or an acute anxiety disorder that impairs function would be treated within the same small habitat where every other crew member lives and works. There is no psychiatric ward, there is no isolation room, there is the habitat, and everyone is in it. The implications compound when you consider that the same small crew responsible for medical care is also responsible for every other critical function. The person performing emergency surgery on Tuesday may be the person repairing the water recycler on Wednesday and conducting a reactor safety inspection on Thursday. There is no specialization luxury. Every crew member is cross-trained in multiple disciplines because the settlement cannot afford to have any single function dependent on a single individual. If one person becomes incapacitated, their responsibilities must be absorbed by the remaining crew. If two people become incapacitated simultaneously, the settlement may be unable to maintain all critical systems. Emergency scenarios beyond medical events carry the same weight. A pressure breach in the habitat, whether from micrometeorite impact, structural fatigue, or a ceiling failure, would require immediate response. The crew must locate the breach, isolate the affected compartment, repair the seal, and repressurize, all while wearing emergency breathing equipment in a module that may be losing air. Fire is an even more insidious threat. In a sealed, oxygen-managed environment, fire behaves differently than on Earth. It can spread through ventilation systems. Smoke fills enclosed spaces rapidly with no natural dissipation. The combustion products are immediately toxic. Firefighting must be conducted inside the same atmosphere the crew is breathing, and the fire suppression systems must extinguish the flame without depleting the habitat's oxygen supply or introducing chemicals that contaminate the life support system. A reactor emergency would be the most consequential of all. If the primary reactor experiences a control failure or a coolant leak, the crew must execute shutdown procedures that halt the fission reaction and stabilize the system. A loss of reactor power triggers cascading failures across every other system. Heating stops, air recycling stops, water purification stops, lighting fails. The backup reactor, if one exists, must be brought online before temperatures drop below survivable levels, which at Europa's surface temperature gives the crew a window measured in hours, not days. Every member of the crew would need to be trained in reactor emergency response, a discipline that on Earth requires years of specialized education and regular recertification. On Europa, the training occurs during the transit phase, and the crew must retain and execute it under conditions of maximum stress with no external support. The cumulative effect of all these constraints is a settlement where every system depends on every other system, and every person depends on every other person. There is no redundancy in the human crew. Each individual represents an irreplaceable concentration of training, capability, and labor. The loss of any one crew member, whether through medical emergency, accident, or psychological incapacitation, does not merely reduce the settlement's capability, it threatens its viability. The remaining crew must redistribute the lost person's responsibilities across fewer people who are already working at capacity. The margin for error, which was already thin, becomes thinner. Construction of the entire settlement would unfold under conditions that make every task harder, slower, and more dangerous than the equivalent operation on Earth, the Moon, or Mars. Every surface excursion exposes workers to radiation, limiting the total time any individual can spend outside the habitat. These limits would be strict, depending on the location on Europa's surface and the effectiveness of the suit shielding. A surface worker might be restricted to shifts measured in hours per week, not hours per day. Complex construction tasks that on Earth might take a crew several days could stretch across weeks or months on Europa, simply because the allowable exposure time is so short. The low gravity complicates physical labor in unexpected ways. At 13% of Earth gravity, lifting heavy objects is easier, but controlling them is harder. Mass still has inertia. A heavy module that weighs very little can still crush a worker if it starts moving and cannot be stopped. Tools behave differently. Fasteners designed for Earth gravity may not seat properly. Dust and ice particles kicked up during excavation settle slowly, drifting through the near vacuum and potentially coating visors, instruments, and seals. The behavior of materials at cryogenic temperatures is often counterintuitive. Metal components that flex normally at room temperature become rigid and brittle. Seals designed to be airtight may contract and leak. Adhesives formulated for terrestrial conditions may fail entirely. Every repair, every modification, every expansion of the settlement must be planned around these constraints. The crew cannot simply walk outside, assess a problem, and fix it. They must schedule the excursion, suit up in heavily shielded protective equipment, limit their exposure time, carry all necessary tools, complete the work within a radiation-safe window, and return to the habitat for monitoring. If the repair takes longer than expected, the worker must retreat and wait for their radiation budget to reset before continuing. If an emergency requires immediate surface access, someone must accept an elevated dose, gambling their long-term health against the short-term survival of the settlement. There would be no warehouses of spare parts, no hardware stores, no supply chains stretching back to factories and mines. Everything the settlement needs must either be brought from Earth at a cost of thousands of dollars per kilogram in launch mass, or manufactured on site from local materials using equipment that itself must be transported, assembled, powered, and maintained. Three-dimensional printing and in-situ resource utilization are promising technologies, but they have never been demonstrated at the scale or in the conditions that Europa would demand. The gap between laboratory prototypes and field-proven systems capable of operating at -160 degrees Celsius under constant radiation bombardment is enormous. What emerges from all of this is a picture of a settlement that is not a colony in any familiar sense. It is a life support machine, a sealed, buried, reactor-powered system that must function perfectly and continuously to keep its occupants alive. Every subsystem depends on every other subsystem. Power feeds heating, which maintains temperature, which keeps water liquid, which supports agriculture, which feeds the crew, who maintain the reactor, which provides power. Break any link in that chain and the entire system degrades toward failure. The crew lives inside this machine. They eat what it grows, they breathe what it recycles, they drink what it purifies. They are warmed by its reactors, shielded by its walls, connected to Earth by its antennas. They cannot step outside without risking their health. They cannot grow their settlement without exposing themselves to the very environment they are hiding from. They are alive because the machine works. If the machine stops, they stop. This is not a frontier homestead. It is not a research station with difficult conditions. It is the most total dependence on artificial life support that any human community has ever contemplated. A submarine crew can surface. A space station crew can evacuate to Earth in hours. An Antarctic team can be rescued by aircraft. A Europa settlement crew has no exit. The nearest help is over 500 million kilometers away. The escape vehicle, if one exists, takes years to arrive. If something goes catastrophically wrong, the settlement does not call for help. It sends a message, waits an hour for acknowledgement, and solves the problem itself or does not solve it at all. And all of this, every watt of power, every litre of recycled water, every controlled breath of filtered air, every carefully rationed minute of surface time, every sleepless night spent monitoring a reactor, cooling loop, or nursing a crew member through a medical crisis, with no specialist to consult, serves a single purpose: surviving long enough to attempt the thing that brought humans to Europa in the first place. Reaching the ocean. That challenge is next, and it may be the hardest problem of all. Everything about Europa leads downward. Every reason to go there, every dollar spent on mission design, every hypothesis about biology and chemistry and the possibility of life beyond Earth, all of it converges on a single destination that no human and no machine has ever reached: the ocean. And reaching it may be the hardest thing our species has ever attempted. Begin with the problem as a physical object. Between the surface where a settlement would huddle inside its shielded bunker and the ocean where the science actually matters lies an ice shell whose thickness, based on the most recent measurements, averages roughly 29 kilometers of rigid conductive ice, with the possibility of additional warmer convective ice beneath that. Set aside the uncertainties. Take the conservative middle estimate. Call it 25 kilometers. That is 25,000 meters of frozen water, compressed under its own weight, riddled with fractures in the upper portions, but increasingly solid and featureless as depth increases and pressure mounts. No one has ever drilled 25 kilometers into anything on any world. The concept of penetrating that distance through ice in a vacuum, at cryogenic temperatures, on a body with 13% of Earth's gravity, powered by a reactor located on a surface blasted by radiation, with no supply chain and no rescue capability, is not merely difficult, it sits at the outer boundary of what current engineering can even model, let alone accomplish. But engineers have been thinking about it for decades, and the leading concept is a device called a cryobot. A cryobot is a thermal probe. Rather than mechanically drilling through ice with rotating bits, it melts its way down. The principle is straightforward. A heated nose cone at the front of the probe liquefies the ice in contact with it. The meltwater flows around the body of the probe and refreezes behind it, sealing the borehole as the device descends. The probe sinks through the ice under its own weight, assisted by the low but non-zero gravity, leaving no open shaft behind it. In theory, this approach avoids many of the problems associated with mechanical drilling. There are no drill bits to wear out, no cuttings to remove, no open hole to maintain against collapse. The cryobot simply melts, sinks, descending meter by meter through the frozen shell until it reaches liquid water. Prototypes have been tested on Earth. The most notable is the Valkyrie probe, developed by Stone Aerospace in Austin, Texas, with funding from NASA. Valkyrie uses a high-power hot water jet system rather than a simple heated nose cone. Pressurized hot water is pumped to the melt head, where it sprays against the ice face, liquefying it rapidly. The melt water is then recirculated, reheated, and sent back to the cutting face in a closed loop. This approach achieves faster descent rates than passive thermal conduction alone. Stone Aerospace tested Valkyrie in the Matanuska Glacier in Alaska, where the probe successfully penetrated ice and demonstrated autonomous descent, navigation, and communication through a fiber optic tether. The results were encouraging. Valkyrie proved that a thermal probe could descend through glacial ice, maintain orientation, communicate data back to the surface, and operate with a degree of autonomy. But the test conditions diverge from Europa's reality in almost every measurable way. Matanuska Glacier ice sits near the melting point, warmed by geothermal heat and seasonal temperature cycles. Europa's surface ice is approximately minus 160 degrees Celsius, over 150 degrees colder. Ice at that temperature requires far more energy to melt per unit volume, because the probe must first warm it from cryogenic temperatures to 0 degrees Celsius before phase change even begins. The energy budget for Europan descent is dramatically higher than for any terrestrial glacier. The Matanuska tests reached depths measured in tens of meters. Europa requires tens of kilometers. The scaling factor between a successful terrestrial test and the actual mission requirement is roughly 1,000 to 1. In engineering terms, that is not an incremental step. It is a generational leap, comparable to the difference between the Wright brothers' first flight and a transatlantic airliner. Both involve heavier-than-air powered flight. The principles are the same. The execution is separated by decades of development. Other concepts have been proposed. NASA's Jet Propulsion Laboratory has studied alternative designs that would combine thermal melting with mechanical cutting to handle ice that may contain rocky debris, salt inclusions, or other non-ice materials that a purely thermal system cannot melt. Some proposals incorporate nuclear heating, using a small radioisotope thermoelectric generator or reactor integrated into the probe body to provide continuous thermal power without any surface tether. These designs eliminate the cable problem entirely, but require miniaturizing nuclear systems to fit inside a probe body roughly the size of a large torpedo, while maintaining enough thermal output to melt through cryogenic ice for years. The first problem common to all designs is power. Melting ice requires energy, and the amount of energy scales directly with the volume of ice that must be liquefied and the temperature deficit that must be overcome. A cryobot with a nose cone roughly 20 centimeters in diameter, melting through Europa's cryogenic ice at a descent rate of approximately 1 meter per hour, would require continuous thermal power on the order of several kilowatts, directed into the melt head. That does not sound like much until you multiply it by the time required. At 1 meter per hour, descending 25 kilometers takes 25,000 hours, which is approximately 2 years and 10 months of continuous operation. If the descent rate is slower, and many models suggest it would be due to the extremely cold ice temperatures on Europa. The timeline stretches to 5, 7, or even 10 years. Think about what that timeline means in human terms. A cryobot deployed at the start of a settlement's operational phase might still be descending through ice when the crew's planned mission duration expires. The settlers could spend their entire tour on Europa maintaining the systems that support the probe, monitoring its glacially slow progress, and transmitting depth readings back to Earth, without the probe ever reaching water. The scientific payoff, the entire justification for the mission, might arrive years after the crew has departed, if they can depart, or might not arrive within any single generation of settlement at all. The probe becomes a multi-decade infrastructure project, sustained across crew rotations, each new team inheriting a borehole they did not start and may not live to see completed. Year 1 of a descent might look like this. The probe is deployed through a surface access shaft excavated by the settlement's construction robots. It activates its thermal system and begins melting into the ice. Progress is measured in meters per day. The crew monitors telemetry through the fiber optic tether, temperature readings, power consumption, descent rate, ice composition data from onboard sensors. At the end of the first year, the probe has descended roughly 8 to 9 kilometers if the 1 meter per hour rate holds steady. That is significant progress in absolute terms, but only a third of the way to the ocean. The data flowing back describes the thermal gradient of the upper ice shell, the distribution of fractures and pores in the near-surface region, and the transition into denser, more uniform ice at depth. Scientifically valuable, operationally routine. The crew's primary task during this phase is maintenance, keeping the surface power station running, monitoring the tether integrity, and managing the settlement's own life support systems. Year 2, the probe passes the 10-kilometer mark. Ice at this depth is warmer than the surface, but still far below freezing, perhaps minus 100 degrees Celsius depending on the thermal gradient. The fractures and pores that characterize the upper shell have largely disappeared. The ice is more homogeneous. Descent may actually accelerate slightly, as the probe encounters warmer material that requires less energy to melt, but new risks emerge. At greater depth, the pressure on the probe increases. The weight of the overlying ice column compresses the surrounding material, which could affect how meltwater flows around the probe body and how effectively the borehole seals behind it. If the ice at depth contains salt inclusions or briny pockets, these could alter the melting dynamics unpredictably. The probe may encounter regions where the ice is not pure water but a mixture of water ice and various salts, creating slush with different thermal properties than clean ice. Year 3. The probe approaches the 20-kilometer mark. If a convective layer exists in the lower ice shell, the probe may now be entering it. Convective ice is warmer and less rigid than the conductive lid above. It may be slowly churning, moving in sluggish convection cells driven by the temperature difference between the frigid surface and the warm ocean below. A descending probe entering a convective zone would experience lateral forces as the ice around it moves horizontally. The probe could be deflected off its vertical path, pushed sideways by ice currents too slow to detect on short timescales but significant over months of descent. Course correction at this depth, with the probe tens of kilometers below the surface and connected to it only by a thread-thin fiber optic line, would be extremely difficult. And somewhere ahead, still kilometers away, lies the ice-ocean interface. The probe's instruments strain to detect it. Temperature readings creep upward. The ice becomes softer. Eventually, the melt rate changes as the probe transitions from solid ice into a zone of increasing slush, partial melt, and finally liquid water. The probe must detect this transition, recognize that it has arrived, and execute a sequence of operations it has been carrying in its memory since launch. Deploy its scientific instruments, activate whatever submersible or sampling system it carries, and begin the actual exploration of Europa's ocean. Throughout that entire multi-year duration, the probe must receive uninterrupted power. A tether connecting the probe to a surface power station is one option, but a cable 25 kilometers long, paying out behind a descending probe through refreezing ice, presents enormous engineering challenges. The cable must remain intact and functional as ice refreezes around it. If the cable snags, kinks, or breaks at any point along its length, the probe loses power and the mission ends. Alternative approaches involve equipping the cryobot with its own onboard power source, most likely a radioisotope thermoelectric generator or a compact nuclear reactor. These devices provide steady heat and electricity independent of any surface connection, but they add mass, complexity, and radiation concerns to a probe that must already carry scientific instruments, communication systems, and possibly a deployable submersible for exploring the ocean once it arrives. Communication with a descending cryobot is another formidable problem. Radio waves do not propagate well through solid ice, especially over distances measured in kilometers. Once the probe descends beyond the first few hundred meters, maintaining contact with the surface becomes extremely difficult. Acoustic communication through ice is possible but limited in bandwidth and reliability. The most practical approach may be a trailing fiber optic cable, which can transmit data and commands through the ice column. But this returns to the cable problem. A fiber optic line 25 kilometers long, threaded through a borehole that is continuously refreezing, must survive years of operation without a single break. One fracture anywhere along that length severs the connection permanently. If the cable fails, or if the mission design excludes a tether entirely, the probe must operate autonomously. It would make every decision about descent rate, obstacle avoidance, power management, and scientific data collection without any human input for years. The probe would store its data internally and transmit it only after reaching the ocean and deploying a relay system back through the ice, assuming it can. This level of autonomy far exceeds anything yet demonstrated in planetary exploration. Every Mars rover ever built has operated with regular ground-in-the-loop command sequences. A Europa cryobot would need to function as a fully independent robotic explorer, making real-time decisions in a completely unknown environment for years at a stretch. The ice itself presents hazards that surface observations cannot fully characterize. Europa's upper ice shell contains fractures, voids, and regions where briny inclusions may create pockets of slushy or liquid material embedded within otherwise solid ice. These features are scientifically interesting but operationally dangerous. A descending cryobot could encounter unexpected voids that cause it to drop uncontrollably, briny layers that alter the melting dynamics, or structural features that deflect the probe sideways off its vertical path. Deeper in the shell, where the ice is under greater pressure and may be slowly convecting, the thermal and mechanical properties change. Convective ice is warmer and softer than the rigid conductive layer above it, which could accelerate descent but also introduces the possibility of lateral currents within the ice that push the probe off course. At the base of the ice shell, where solid ice meets liquid ocean, the transition zone may not be a clean boundary. Modelling suggests that the interface could be a gradual region of increasingly slushy, partially melted material rather than a sharp solid-to-liquid border. The probe must detect this transition, recognize that it has reached the ocean, and prepare for deployment in liquid water, all without getting stuck in a zone of semi-frozen mush that is neither solid enough to melt through cleanly nor liquid enough to swim in. And then there is the constraint that may matter more than all the engineering challenges combined: planetary protection. If Europa's ocean harbours any form of life, even microbial life at the most primitive level, then delivering an Earth-built probe into that ocean without contaminating it with terrestrial organisms becomes a defining requirement. This is not a theoretical concern. It is a binding policy framework governed by international agreements under the Committee on Space Research, known as COSPAR. Europa is classified as a body of high interest for astrobiology, and any mission that contacts its subsurface ocean must meet extraordinarily stringent sterilization standards. The difficulty is that perfect sterilization of a complex mechanical system is essentially impossible. Spacecraft carry microbial hitchhikers in every joint, seal, wire bundle, and fluid line. Some terrestrial microorganisms are extraordinarily resilient. Certain bacterial endospores can survive vacuum, radiation, extreme temperatures, and chemical disinfection. Experiments aboard the International Space Station have demonstrated their survival after 18 months of direct exposure to open space. If even a handful of such organisms reach Europa's ocean aboard a cryobot, they could potentially survive, reproduce, and spread through an environment that may have its own independent biology. The contamination would be irreversible. Once terrestrial microbes enter a liquid ocean with possible chemical energy sources, there is no way to recall them, no way to distinguish them from native life. no way to undo the damage. This means every probe intended to enter Europa's ocean must be sterilized to a standard far beyond anything previously required in spaceflight. Current planetary protection protocols for Mars missions are already considered demanding. Europa ocean access would require sterilization levels orders of magnitude more stringent. The probe's exterior and interior must be essentially free of viable organisms, a condition that conflicts with the practical requirements of building a complex electromechanical system with thousands of components, fluids, lubricants, and sealed compartments where microbes can hide. Some mission designers have proposed using the cryobot's own thermal system as a sterilization mechanism, heating the outer shell to temperatures sufficient to kill any remaining microbes during the initial descent. Others have suggested enclosing the probe in a sterile outer shell that is only breached at the moment of ocean entry. These approaches add complexity and mass to an already challenging design, and they must work perfectly. A 99.9% sterilization rate sounds impressive until you realize that a single surviving spore carried into an alien ocean could compromise the most important scientific discovery in human history. For a crewed settlement, planetary protection becomes even more complicated. Humans are walking ecosystems. Every person carries trillions of microorganisms on their skin, in their gut, in their lungs, in every bodily fluid. A human presence anywhere near the ice-ocean interface introduces contamination risks that are qualitatively different from anything a robotic probe would create. If settlers attempt to access the ocean, either through cryobot deployment or through larger-scale drilling operations, they must do so while managing a biological contamination hazard that is inherent to their own existence. The very bodies of the people who travelled 500 million kilometres to find life on Europa would be the greatest threat to verifying whether that life exists. Assume, despite all of this, that a probe reaches the ocean. Assume the ice is penetrated, the transition zone is navigated, and a functioning submersible or sensor package is deployed into liquid water beneath 25 or more kilometers of ice. What does it find? Darkness. Complete, absolute, permanent darkness. Europa's ocean receives no sunlight. The ice shell is opaque. Below the first few meters, no photon from the sun has penetrated this water in the entire history of the solar system. Whatever exists in this ocean has existed in darkness for billions of years. For a human observer or a robotic camera, the ocean would be visible only within the range of whatever artificial light source the probe carries. Beyond that cone of illumination, there is nothing. No seafloor visible from the surface. No surface visible from the seafloor. Just water extending in every direction, black and featureless, for potentially tens of kilometers in depth. The submersible itself would need to be an extraordinary machine. It would carry sonar for mapping in zero visibility, because optical cameras are useless beyond the range of onboard lighting in water that has never seen light. It would carry chemical sampling instruments capable of analyzing water composition, salinity, pH, dissolved gas content, and the presence of organic molecules. It would carry pressure-tolerant housings for its electronics, rated to withstand conditions ranging from roughly 200 bars near the ice-ocean interface to potentially over 1,000 bars at the seafloor. It would need propulsion, navigation, obstacle avoidance, and the ability to operate for weeks or months in an environment where no external reference points exist, no surface is visible, and no signal from the settlement can reach it through 25 kilometers of solid ice above. If the submersible is tethered to the cryobot, which remains lodged at the base of the ice shell, its range is limited by cable length. If it is untethered, it must navigate autonomously, make its own decisions about where to explore, how to sample, and when to return to the ice-ocean interface for data upload. In either case, it must eventually transmit its findings upward through the ice column to the surface. This requires either the fiber optic tether to remain intact over the entire ice thickness, or an acoustic relay chain embedded at intervals through the refrozen borehole. Neither approach has been tested at these scales or in these conditions. The data the submersible collects might take days or weeks to transmit back through the ice, even assuming the relay works. The settlement crew, sitting in their buried habitat on the surface, would receive fragmentary updates about conditions in an ocean they cannot see, touch, or directly interact with. They would analyze chemical readings, sonar maps, and temperature profiles, assembling a picture of an alien environment from numbers on a screen. If the instruments detect something remarkable, an unexpected chemical signature, a thermal anomaly, a pattern in organic molecule distribution that does not match abiotic processes, the crew would know that they might be looking at the most important data in human history, but they would not know for certain. Confirming the discovery of extraterrestrial life requires multiple lines of evidence, repeated measurements, control experiments, and independent verification. All of that takes time and capabilities that a small probe in a dark ocean 25 kilometers below a radiation-blasted ice surface may not possess. To understand how much remains unknown about Europa's ocean, it helps to compare it with the one other place in the outer solar system where we have actually sampled ocean material directly: Enceladus, Saturn's sixth largest moon. Enceladus is much smaller than Europa, only about 500 kilometers in diameter, but it does something Europa has not been confirmed to do. It vents material from its subsurface ocean directly into space through dramatic plumes erupting from fractures near its south pole. The Cassini spacecraft, which orbited Saturn from 2004 to 2017, flew through those plumes multiple times and analyzed their composition with onboard mass spectrometers. The results transformed our understanding of ocean worlds. Cassini detected water vapor and ice particles, as expected, but it also found sodium chloride salts, indicating a salty ocean in contact with rock. It detected silica nanoparticles, which on Earth form only in hot water interacting with silicate minerals, strong evidence for hydrothermal activity on Enceladus's seafloor. Most significantly, Cassini detected molecular hydrogen in the plume material. On Earth, molecular hydrogen in ocean environments is primarily produced by serpentinization, the reaction of water with iron, and magnesium-rich minerals at elevated temperatures. This process occurs at hydrothermal vents and provides chemical energy that entire microbial ecosystems exploit. Finding molecular hydrogen at Enceladus meant the ocean likely had active water rock chemistry, producing the very fuel that terrestrial life uses for metabolism. Cassini also detected complex organic molecules in the ice grains ejected from Enceladus. Some of these molecules had masses exceeding 200 atomic mass units, suggesting carbon-rich chemistry more elaborate than simple methane or carbon dioxide. The combined picture, salt water, hydrothermal activity, molecular hydrogen, and complex organics, made Enceladus one of the most compelling astrobiological targets in the solar system. And all of this was learned because Enceladus conveniently sprays its ocean contents into space where a passing spacecraft can collect them. Europa offers no such convenience. The plume evidence at Europa, as discussed earlier, has weakened considerably. Even if intermittent plumes do occur, they appear far less vigorous than Enceladus's south polar jets, which sustain Saturn's E-ring with a continuous supply of ice particles. Europa may occasionally burp small quantities of water vapor through surface cracks, or it may not. The 2026 reanalysis of Hubble data reduced confidence in the original detection to below 90%. The James Webb Space Telescope found no plume signatures during its observations. This means the approach that worked brilliantly at Enceladus, simply flying through the spray and tasting the ocean, is likely unavailable at Europa. Whatever Europa's ocean contains, it keeps to itself, sealed beneath kilometers of ice that permit no easy sampling. Every piece of information about ocean composition must be obtained either indirectly through surface spectroscopy and geophysics, or directly by penetrating the ice shell, which requires the multi-year cryobot descent just described. Europa is the harder target despite being the more famous one. Enceladus showed scientists what an ocean world can reveal when it cooperates. Europa shows what happens when it does not. The pressure in Europa's ocean is substantial. At the ice-ocean interface, the weight of the overlying ice shell creates a pressure of approximately 20 to 30 megapascals, equivalent to roughly 200 to 300 times Earth's atmospheric pressure at sea level. This is comparable to conditions at moderate depths in Earth's oceans, around 2 to 3 kilometers down. A well-designed submersible could handle this. But if the ocean extends to depths of 60 to 100 kilometers, as some models suggest, the pressure at the rocky seafloor could reach 130 to 150 megapascals, exceeding even the deepest trenches on Earth. Equipment designed for the upper ocean might not survive a descent to the bottom. The temperature is near or just below the freezing point of salt water, probably somewhere between -2 and -4 degrees Celsius, depending on salinity and pressure. This is cold by terrestrial standards, but not prohibitively so for engineered systems. Earth's deep oceans reach similar temperatures. The critical difference is not the cold itself, but the combination of cold, darkness, pressure, distance from support, and total isolation. A submersible operating in Europa's ocean would be the most remote human-built object in history. It would be farther from help than any machine has ever been. The nearest human being would be 25 kilometers straight up through solid ice, inside a buried habitat, on a world more than 500 million kilometers from Earth. The ocean's chemistry remains largely unknown. Models suggest the water contains dissolved salts, possibly magnesium sulfate, sodium chloride, and other ionic compounds, but the exact composition has never been directly measured. The salinity could range from a few parts per thousand to concentrations approaching 10 to 30% of Earth's seawater, depending on which models you trust. The pH is uncertain. The dissolved gas content is uncertain. The presence or absence of organic molecules is uncertain. Almost everything scientists believe about Europa's ocean chemistry is inferred from surface spectroscopy, magnetometer data, and theoretical models rather than direct sampling. What is somewhat better constrained is the energy landscape. The ocean sits between two potential sources of chemical energy. From above, Jupiter's radiation processes surface ice into oxidants like molecular oxygen and hydrogen peroxide, which could theoretically be transported downward through the ice shell to the ocean. From below, the rocky seafloor may host water-rock reactions, particularly a process called serpentinization, in which water reacts with iron and magnesium-rich minerals to produce molecular hydrogen. On Earth, serpentinization at hydrothermal vents supports entire ecosystems of microorganisms that metabolize hydrogen for energy, completely independent of sunlight. If both processes operate on Europa, the ocean could contain a redox gradient, a chemical energy slope that life could exploit. Oxidants from above and reductants from below, meeting in the ocean water, would create the kind of chemical disequilibrium that biological systems on Earth have learned to harvest. This is the theoretical foundation for Europa's habitability argument. It is elegant, physically plausible, and entirely unconfirmed. The 2024 Juno measurement complicates the oxidant side of this equation. If Europa's surface produces only about 12 kilograms of oxygen per second, and only a fraction of that oxygen is retained in the surface ice rather than escaping to space, then the total supply of oxidants available to be transported to the ocean is smaller than many earlier estimates assumed. The transport mechanism itself is uncertain. Surface ice must somehow move downward through the shell to deliver its chemical cargo to the liquid water below. For years, scientists lacked a convincing explanation for how this downward transport could work. The ice shell's geological activity, driven by tidal forces, mostly shuffles material laterally rather than vertically. In January 2026, a study published in the Planetary Science Journal proposed a new mechanism. Geophysicists at Washington State University modeled a process inspired by crustal delamination on Earth. On our planet, dense portions of the lower crust can detach and sink into the mantle when they become heavier than the surrounding rock. The Europa team proposed that something similar could happen in the ice shell. Jupiter's radiation processes surface ice into salt-rich, chemically altered material that is denser than the pure ice surrounding it. Previous laboratory work had shown that these impurities also weaken the crystalline structure of the ice. The combination of greater density and reduced structural strength could allow patches of this nutrient-laden surface ice to detach from the surrounding shell and sink downward through the warmer, softer ice below. The team's computer models showed that for a broad range of salt concentrations, dense surface ice could sink all the way to the base of the shell, provided there was at least modest weakening in the source region. The process could operate on relatively short geological timescales and might function as a recurring conveyor belt, continuously delivering radiation-processed material from the surface to the ocean. This is a promising hypothesis, but it is a hypothesis supported by computer modeling, not by direct observation. No one has watched this process happen. No instrument has measured downward ice transport on Europa. The models depend on assumptions about ice rheology, salt concentrations, grain-scale mechanical properties, and thermal profiles that remain poorly constrained. The mechanism is physically plausible and consistent with what is known about Europa's surface composition, but it has not been confirmed. The distinction matters because the entire habitability argument depends on whether oxidants actually reach the ocean in meaningful quantities. From below, the evidence for hydrothermal activity is similarly circumstantial. No vent has ever been observed on Europa's seafloor. No direct measurement of seafloor temperature, chemistry, or geological activity has ever been made. The hypothesis rests on analogy. Earth has hydrothermal vents at spreading ridges where tectonic plates pull apart. Europa has tidal heating that warms its rocky interior. If that heating is sufficient to drive fluid circulation through the mantle rock, water-rock reactions could produce hydrogen and other reduced compounds, creating the chemical energy that life might exploit. But the tidal heating rate in Europa's rocky interior is not well constrained. Some models suggest enough heat to drive active volcanism on the seafloor. Others suggest only modest warming insufficient for vigorous hydrothermal circulation. As the Enceladus comparison demonstrated, the molecular hydrogen found in those plumes provided the strongest evidence yet for active hydrothermal chemistry on an ocean world. No equivalent detection has been made at Europa, partly because Europa may not be venting material that can be sampled from orbit. So here is what the ocean actually offers a human settlement: a body of liquid water that almost certainly exists based on multiple independent lines of evidence. A chemical environment that might contain the ingredients for life, based on surface spectroscopy, theoretical models, and analogy with Earth. A possible energy source from below, based on plausible but unconfirmed assumptions about interior heating. A possible nutrient supply from above, based on a modelling study published less than a year ago. And a potential biosphere that has never been directly observed, sampled, measured, or confirmed by any instrument ever built. The ocean is the reason for going. It is the scientific prize that justifies the radiation exposure, the reactor dependence, the confinement, the isolation, and the cost. And it is locked behind a barrier that would take years to penetrate using technology that has never been tested beyond laboratory prototypes, protected by sterilization requirements more stringent than anything ever implemented, accessible only through a borehole that closes behind the probe as it descends, leading to an environment so remote that the probe may never be able to report what it finds. Compare this with what Cassini accomplished at Enceladus, a spacecraft launched in 1997, built with 1990s technology, flying through plumes at speeds of kilometers per second, captured enough information with onboard mass spectrometers to confirm an ocean, detect hydrothermal chemistry, identify complex organics, and fundamentally reshape the search for life in the outer solar system. No landing required, no drilling, no cryobot, no multi-year descent. The ocean came to Cassini. At Europa, nothing comes to you. You must go to the ocean, and the ocean is buried beneath the largest barrier of ice in the inner solar system. And even if you spend a decade getting there, you may contaminate the very thing you came to find. A settler on Europa would know all of this. They would live inside their shielded habitat, eating hydroponic greens under artificial light, breathing recycled air, rationing their surface time to avoid radiation exposure, maintaining their reactor with dwindling spare parts, communicating with Earth in hour-long silences, and they would know that directly beneath them, separated by a distance that a cryobot might need half a decade to traverse, lies the most scientifically significant body of water in the known universe. An ocean that might contain living organisms. An ocean that might answer the oldest question humanity has ever asked. An ocean they can detect through instruments, model on computers, theorize about in papers, and argue about during the long hours of confinement. But they almost certainly cannot reach it. Not with the equipment they brought, not within the time frame of a single human mission, not without risking the contamination of the very environment they crossed the solar system to study. The ocean would hover beneath their awareness like a signal just beyond the range of the receiver, always implied, always tantalizingly close in astronomical terms, always functionally out of reach in human ones. That is the particular cruelty of Europa. It does not lack what humans are searching for. It possesses it in abundance and then locks it away beneath the most formidable natural barrier in the solar system. The ice is not just a physical obstacle, it is a temporal one. It takes so long to penetrate that the question of whether the ocean contains life becomes entangled with the question of whether the settlement can survive long enough to find out. The ice transforms a scientific question into an endurance test, and the test may outlast the participants. And for the humans living above it, confined to their buried habitat, dependent on their machines, counted down by their radiation budgets, the ocean would define every waking hour without ever being experienced directly. What that life would actually feel like, hour by hour, day by day, inside the most isolated human settlement ever conceived, is what comes next. You wake up, and the ceiling is close. Not uncomfortably close, not brushing your face, but close enough that the first thing you register every single morning is that you are inside something. The walls are curved, insulated, lined with conduit and monitor screens. The light is artificial, a blue-white spectrum calibrated to simulate terrestrial daylight rhythms, but your body knows the difference. There is no warmth on your skin from a window. There is no change in the quality of the light as clouds move, or as the angle of illumination shifts through the hours. The light switches on, the light switches off. The cycle repeats. It has repeated every day for months. It will repeat every day for years. You swing your legs off the bunk, and your feet touch the floor too gently. The gravity here is roughly 13% of what your body expects. You weigh about 1/7 of what you weighed on Earth. Your muscles do not need to strain. Your heart does not need to pump as hard. Your skeleton does not bear the same load. Every physiological system that evolved under Earth's gravitational field is slowly, quietly atrophying. You have been exercising for 2 hours every day on resistance machines specifically designed to stress your muscles and bones against forces they would otherwise never experience here. The machines work. They slow the decline. They do not stop it. Long-duration studies aboard the International Space Station, conducted in microgravity, demonstrated that even with rigorous daily exercise, astronauts lose roughly 1 to 2% of bone mineral density per month in weight-bearing bones. The effects of partial gravity at 13% of Earth's are unknown. No human has ever lived in this gravitational regime for more than a few hours. You are the experiment. What is known is troubling. Bone loss in reduced gravity is not merely a structural problem. It releases calcium into the bloodstream, which can contribute to kidney stones, a medical emergency that on Earth involves imaging, pain management, and sometimes surgical intervention. On Europa, it involves whatever the settlement's medical officer can do with the equipment on hand. Those medical constraints become personal here. A kidney stone formed from the calcium your thinning bones have released into your bloodstream is not a routine problem when the nearest imaging equipment capable of locating it does not exist. A cardiac event is not a routine problem when the communication delay means any advice from Earth arrives over an hour after you requested it. An allergic reaction is not a routine problem when the pharmacy is a finite pre-packed supply selected years before launch. Every medical scenario on Europa plays out against the same unforgiving arithmetic. Limited tools, limited expertise, and no possibility of evacuation. Cardiovascular deconditioning is another silent threat. In lower gravity, the heart does not work as hard to circulate blood. Over months and years, the cardiac muscle can weaken, and the body's fluid distribution shifts, moving blood and other fluids toward the upper body and head. On the International Space Station, this shift contributes to a condition called spaceflight-associated neuroocular syndrome, where increased intracranial pressure affects vision. Some astronauts have returned to Earth with permanently degraded eyesight after missions lasting 6 to 12 months. At 13% gravity, the effect might be less severe than in microgravity, or it might manifest differently in ways no one can predict. If a crew member's vision deteriorates significantly during a multi-year stay on Europa, there is no corrective procedure available, no return flight within weeks, and no ophthalmologist closer than 500 million kilometers. Muscle atrophy compounds the problem. Even with exercise, the body adapts to the load it actually experiences. Muscles that are not challenged shrink. Tendons that are not stressed weaken. The postural muscles that keep you upright on Earth have almost nothing to do at 13% gravity. Over years, a settler's body would reshape itself for Europa's gravitational environment, becoming progressively less capable of functioning under Earth gravity. Return to Earth, if it ever happened, would be physically devastating. The settler's heart, bones, muscles, and vestibular system would all be tuned to a world 1/7 as heavy as the one they came from. And this is where the return problem reveals its full cruelty. The mission is nominally round-trip. A transit vehicle waits in orbit or on the surface, fueled and ready for the journey home. In theory, the crew completes their tour, boards the vehicle, and begins the 3 to 6 year cruise back to Earth. But consider the physical reality of that return. A crew member who has spent 2 or 3 years on Europa at 13% gravity boards, a transit vehicle that provides either microgravity or, at best, partial artificial gravity from a rotating module that has never been tested for multi-year habitation. During the return cruise, the body does not recover. It continues to adapt to whatever gravitational regime the spacecraft provides. If that regime is microgravity, the bone loss and cardiovascular deconditioning that accumulated on Europa continue to worsen. If the spacecraft provides some rotation-based gravity, it may slow the decline but cannot reverse years of adaptation to a lighter world. At the end of the return transit, the crew arrives at Earth. They must endure re-entry deceleration forces of 3 to 4 times Earth's gravity, sustained for minutes, in bodies that have not experienced even 1 full G for 5 to 8 years. The cardiovascular system, weakened by years in reduced gravity, must suddenly pump blood against a gravitational load it has forgotten how to handle. The skeleton, thinned by years of calcium loss, must support a body weight it was no longer built to carry. The muscles that atrophied on Europa and further weakened during transit must suddenly bear the full burden of terrestrial gravity. Astronauts returning from 6-month International Space Station missions require assistance to stand and walk for days afterward. Astronauts returning from year-long missions report weeks of rehabilitation before basic mobility returns. A crew returning from 5 to 8 years of reduced and microgravity faces a reintegration timeline measured in months at minimum, with no guarantee of full recovery. Some damage may be permanent. The bones that thinned may never fully rebuild. The vision that degraded may never fully restore. The cardiovascular capacity that diminished may never return to pre-flight levels. The mission was designed as a round trip. The human body may experience it as a one-way journey from which Earth normal function cannot be recovered. This raises the question that lurks beneath every discussion of Europa settlement and is almost never stated openly. Who volunteers for this? The answer, based on decades of astronaut selection psychology and analog mission research, is specific and narrow. The people who would be considered for a Europa mission would not be adventurers in the romantic sense. They would not be adrenaline seekers or frontier dreamers drawn by the thrill of the unknown. Those personality types consistently perform poorly in long-duration isolation studies. They become restless, agitated, and prone to conflict when the novelty fades and the monotony sets in. The people who thrive, or at least endure, in isolated, confined environments tend to share a constellation of traits that selection psychologists have studied for decades. High emotional stability, low need for external stimulation, strong internal motivation that does not depend on recognition or reward, the ability to find meaning in routine work, comfort with silence, tolerance for interpersonal friction without escalation, and critically, the capacity to accept conditions they cannot change without surrendering the will to function. These traits describe a specific and rare psychological profile. Selection programs for long-duration missions already screen for these qualities, but a Europa mission would push the requirements far beyond anything previously demanded. The crew must not merely tolerate isolation for 18 months, as in a Mars transit simulation. They must tolerate it for years, in a smaller space, with greater danger, longer communication delays, no possibility of evacuation, and the knowledge that their bodies are being permanently altered by the environment. The psychological contract is unlike any other in human exploration. Every previous expedition, from polar exploration to orbital spaceflight, preserved at least the theoretical possibility of return to normal life. A Europa mission may not. The volunteers must accept that possibility before launch. They must accept it again every morning they wake up inside the habitat, and they must continue functioning at a high level despite that acceptance. This is the body's slow betrayal in low gravity, and the mind's slow siege in confinement. But the sensory environment adds a third dimension of erosion that compounds both. The habitat is small. Concepts for deep space settlement modules typically propose pressurized volumes measured in hundreds of cubic meters, not thousands. The crew lives, works, eats, sleeps, and exercises within a space comparable to a modest apartment shared by everyone. Privacy is architectural fiction. Walls between compartments provide acoustic separation but not true solitude. Every conversation, every argument, every moment of frustration or grief or laughter occurs within earshot of people you did not choose, cannot leave, and will live alongside for years. There is no sky. This sounds like a minor deprivation until you consider how deeply the human nervous system depends on environmental openness. The experience of looking upward, of seeing clouds or stars or even an overcast ceiling of grey, activates neural circuits associated with spatial orientation, emotional regulation, and stress recovery. Research in environmental psychology consistently shows that access to views of nature or open sky reduces cortisol levels, improves mood, and supports cognitive performance. A Europa habitat offers none of this. The ceiling is always there, the walls are always close, the lighting is always artificial, the outside is always lethal. Underground isolation studies provide the closest terrestrial analogue for what Europa's settlers would experience, and the findings are not reassuring. In 1962, French geologist Michel Siffre descended into a subterranean glacier cave in the Alps and lived alone in darkness for 2 months without any time cues. His internal clock rapidly desynchronized from the 24-hour cycle. He experienced severe disorientation, depression, and cognitive slowing. His sense of time was distorted so severely that when researchers told him the experiment was over after 60 days, he believed only 34 had passed. Subsequent underground isolation experiments, some lasting as long as 6 months, confirmed these findings across multiple subjects. Without natural light cues, the human circadian system drifts. Modern research places the intrinsic human circadian period at approximately 24.2 hours, only slightly longer than a standard day, but enough to cause progressive desynchronization over weeks and months of isolation. Sleep quality degrades. Alertness fluctuates unpredictably. Mood disorders become more frequent and more severe as the isolation continues. Europa would intensify every aspect of this problem. The settlers would not merely be underground, they would be underground on another world, sealed inside a pressurized compartment, in an environment where the surface above them is lethal and the ice beneath them extends for tens of kilometers. The sense of enclosure would not be psychological alone. It would be physical, absolute, and inescapable. There would be no emerging into daylight after the experiment ends. There would be no experiment endpoint visible on the calendar. There would be the habitat, and the habitat would be the entire world for years. There are no seasons, no weather, no variation in the daily sensory environment beyond what the crew deliberately creates. On Earth, even the most monotonous environments change. The wind shifts, the temperature rises and falls, rain comes and goes. On Europa, inside the habitat, the environment is controlled, constant and unchanging. The same temperature, the same humidity, the same air pressure, the same recycled air with its faint mechanical undertone from the ventilation system. Day after day after day, the senses receive the same inputs. The brain, deprived of novelty, begins to slow. Attention wanders. Motivation declines. Tasks that once felt purposeful begin to feel mechanical. The psychological literature calls this stimulus deprivation. Submarine crews call it going stale. Whatever the name, it corrodes human functioning over time, and on Europa the timeline extends far beyond anything previously studied. Studies of isolated, confined environments on Earth provide consistent warnings about what happens to small groups under these conditions. Antarctic winter-over crews at stations like Concordia, which houses 13 people through months of polar darkness, report increased irritability, sleep disruption, cognitive slowing, and interpersonal tension that builds as the isolation continues. Submarine crews, confined for months in enclosed spaces with no natural light, show similar patterns. These effects are collectively termed third quarter syndrome, a deterioration in morale and performance that typically peaks around the 3-quarter mark of a mission's duration. The phenomenon has been documented in virtually every long-duration isolation study ever conducted. The Mars 500 experiment, which confined 6 volunteers in a simulated spacecraft for 520 days in Moscow, observed reduced activity levels, disrupted sleep cycles, and interpersonal withdrawal that worsened progressively over the mission duration. On Europa, the isolation is not for months. It is not for 520 days. It is for years. And the psychological stresses are compounded by factors that no Antarctic station, submarine crew, or simulation facility has ever faced. The gravity is wrong. The radiation is real. The medical support is finite. The communication delay is measured in hours. And there is no door that leads outside to fresh air and open sky. Because outside is death. Communication with Earth offers limited relief. The signal delay means conversation is impossible. You can send a message. You can wait. You can receive a reply that addresses the person you were an hour ago, not the person you are now. Over time, this delay erodes the feeling of connection. Studies of long-duration spaceflight communication show that crew members gradually shift from conversational messages to informational ones, reporting data rather than sharing feelings. The emotional bandwidth narrows. Relationships with people on Earth become increasingly abstract. Family members age. Children grow, friends move on, the settler receives updates about a world that is evolving without them, and their ability to participate in that evolution is limited to time-delayed recordings that arrive like letters from a foreign century. Within the crew, interpersonal dynamics become the dominant social reality. Every personality trait, every habit, every quirk that would be unremarkable in a larger social context becomes magnified by proximity and duration. The crew member who chews too loudly, the one who monopolizes shared equipment, the one who processes stress through silence and the one who processes it through talking. In a city, these differences dissolve into the crowd. In a habitat the size of an apartment, shared by a handful of people for years, they can become sources of conflict intense enough to threaten mission integrity. Every space agency that has studied long-duration isolation has identified interpersonal conflict as one of the highest risks to crew performance. On Europa, there is no counselor to visit, no bar to escape to, no walk around the block to clear your head. The block is the habitat. The walk ends at the wall. Equipment maintenance fills much of the crew's waking life and carries existential weight. Every system in the habitat is a single point of potential failure. The water recycler, the air scrubber, the thermal management system, the reactor cooling loop, the communication antenna, the food production lighting array. Each of these must be monitored, serviced, and repaired continuously. Parts wear out. Seals degrade under radiation and thermal stress. Electronic components accumulate radiation damage and begin to malfunction. On Earth, a broken pump means a call to a supplier and a replacement part within days. On Europa, a broken pump means fabricating a replacement from whatever materials and tools are available, using skills the crew may or may not possess, under time pressure, dictated by how long the habitat can function without that specific system. Some repairs require surface access, an antenna that has been degraded by radiation, a solar sensor used for navigation calibration, an external valve on a thermal radiator. Each of these repairs means a surface excursion, which means radiation exposure, which means the crew member performing the work is spending a portion of their lifetime radiation budget on a maintenance task. The budget is not infinite. Every hour on the surface accumulates dose. Over the course of a multi-year mission, the available surface time for each crew member shrinks as their cumulative exposure rises. Eventually, a crew member may reach their limit, at which point they can no longer go outside at all, regardless of what needs to be repaired. If critical systems fail, and the only people trained to fix them have exhausted their radiation allowance, the settlement faces a choice between accepting equipment degradation and accepting biological damage. This calculus, trading health against function, radiation against repair, individual risk against collective survival, would pervade every operational decision. It is not a dramatic crisis. It is a daily grinding negotiation between human limits and mechanical needs, conducted in an environment that punishes every mistake and forgives none. Now compare Europa to the other destinations humans have discussed colonizing, and the uniqueness of its cruelty becomes clear. The moon is harsh. It has no atmosphere, extreme temperature swings, abrasive dust, and radiation exposure from solar and galactic sources. But it is 3 days from Earth by spacecraft. Resupply is feasible. Evacuation is possible. Real-time communication is available with only a 1.3-second delay. If something goes catastrophically wrong on a lunar settlement, help can arrive within a week. Mars is harder. It has a thin atmosphere, dust storms, radiation, and cold. The communication delay ranges from 4 to 24 minutes one way. Resupply takes months. Evacuation windows open only every 26 months. Mars is genuinely isolated, but Mars has accessible surface resources. Its atmosphere, thin as it is, provides some radiation shielding and can be processed for breathing oxygen and rocket fuel. Its gravity, at 38% of Earth's, is nearly 3 times stronger than Europa's. And critically, the surface of Mars is the destination. The thing you came to study is right there under your feet, accessible with a shovel and a drill. Europa inverts this relationship entirely. The surface is not the destination. The surface is the obstacle. It is the irradiated, frozen, vacuumed barrier that stands between the settlement and the reason it exists. The ocean below is the destination, and it is buried under kilometers of ice that may take years to penetrate, protected by sterilization requirements that may prevent humans from ever directly interacting with it, and characterized by uncertainties so profound that the probe you send down might find a sterile brine or the most important discovery in human history, and you would have to wait years to find out which. A settler on Mars can walk outside, pick up a rock, and learn something. A settler on the Moon can look up and see Earth hanging in the sky, a visible reminder of home. A settler on Europa can do neither. They live underground, they look at walls, they maintain machines. They wait for data from a probe descending through ice at a rate of 1 meter per hour. The most interesting thing within 1 billion kilometers of their location is directly beneath them, and they cannot touch it, taste it, see it, or reach it without risking the contamination of the very discovery they were sent to protect. This is the psychological architecture of life on Europa. Not danger in the cinematic sense, not meteor strikes or alien predators or dramatic equipment explosions. Confinement, monotony, dependence, the slow erosion of health in a gravity field the body was never designed for. The slow erosion of connection to a home world that drifts further away emotionally with every time-delayed message. The slow erosion of purpose as the years stretch on and the ocean remains just out of reach. And yet, Europa may be one of the most important places in the solar system. The evidence for a subsurface ocean is strong and comes from multiple independent lines of observation spanning decades. The chemistry appears promising, the energy sources are plausible. The conditions at the ice-ocean boundary, and possibly at the rocky seafloor, may fall within the ranges that terrestrial biology considers habitable. If life exists anywhere else in this solar system, Europa is among the most likely places to find evidence of it. That possibility alone justifies the missions now underway. Europa Clipper, currently cruising toward Jupiter for arrival in 2030. JWST, en route for arrival the following year. These robotic emissaries will map the ice, measure the shell, characterize the chemistry, and search for signs of geological activity that might indicate conditions favorable to biology. But robotic flybys and orbital surveys can only take the investigation so far. At some point, if the evidence continues to build, the question will shift from whether Europa is worth studying to whether it is worth inhabiting. Whether the potential payoff, the discovery of extraterrestrial life, or at least the definitive confirmation of habitable conditions beyond Earth, justifies placing human beings inside a sealed bunker on an irradiated ice moon for years at a time, with no certainty of success and no easy path home. The answer depends on what you believe humans are for. If the purpose of human spaceflight is efficiency, then Europa is a poor choice. Robots can tolerate radiation that kills people. Robots do not need food, water, warmth, or psychological support. Robots do not suffer from bone loss or isolation or grief. A robotic probe descending through Europa's ice shell requires no habitat, no reactor, no life support system, and no agonizing decisions about whose radiation budget to spend on the next repair. For pure scientific return per dollar invested, robots win. But humans do not explore solely for efficiency. We explore because the act of going somewhere, of standing in a place no one has stood before, of confronting the unknown with human senses and human judgment, carries a significance that transcends data collection. The settlers who might one day live on Europa would not be there because robots could not do the science. They would be there because humanity decided that some questions are important enough to answer in person, even at extraordinary cost. That cost, on Europa, would be measured in health, in sanity, in years of life spent inside a machine, in the slow surrender of physical capability to a gravity field too weak to sustain the body that evolution built. The settlers would not live beside an ocean under an alien sky. They would live inside shielding, beneath ice or regolith, in sealed compartments, surrounded by radiation monitors, pressure gauges, recycled air, and carefully rationed access to a surface that would damage them every time they touched it. The ocean would remain the central promise and the central frustration, close enough to define the entire mission, buried deeply enough to turn every attempt to reach it into a major engineering and planetary protection problem that might outlast the crew's own mission duration. The settlers would spend their days maintaining the systems that keep them alive, exercising to slow the deterioration of their bodies, eating the same limited crops from the same hydroponic trays, communicating with Earth in transmissions that feel less like conversation and more like time capsules. And beneath all of it, beneath the ice, beneath the frustration, beneath the mechanical routine of survival, the ocean would persist. Dark, pressurized, possibly alive, and almost certainly beyond their reach. Europa does not punish with hostility. It does not rage or storm or strike. Its cruelty is quieter than that. It is the cruelty of proximity without access, of evidence without confirmation, of a door you can detect but not open. The radiation is not personal. The cold is not malicious. The ice is not vindictive. Europa simply exists as it has existed for billions of years, a frozen shell wrapped around a liquid interior, orbiting a gas giant in the outer solar system, indifferent to the fact that one of its chemical environments might contain something that a small, warm, fragile species on the third planet from the Sun has spent its entire conscious history searching for. The settlers would know this. They would understand, in a way that no one on Earth could fully grasp, the precise distance between human desire and physical reality. They would live inside that distance every day, and they would endure it, not because Europa is welcoming, but because what it might contain is worth the endurance. Europa may be one of the best places in the solar system to search for conditions related to life beyond Earth, but it is not a home. It is not a colony waiting to be founded. It is not an ocean world where humans could swim beneath an alien sky. It is a buried promise, wrapped in radiation and ice, guarded by the most formidable natural barrier in the solar system, reachable only by humans willing to live inside a machine, under a frozen ceiling, in the dark, for years, sustained by the possibility that beneath them, in water no sunlight has ever touched, something might be alive. And the deepest cruelty of Europa is not that it might be empty, it is that it might not be. And we may never know, because the world that could answer humanity's oldest question is the same world that would make asking it in person nearly impossible to survive.